I started recording. And can you see my PowerPoint slide?
Yes, sir.
Okay. For today, we will continue our previous discussion. For today, we will concentrate on how to draw the shear and moment diagram. So previously, last week, right? I teach you guys already on how to find the internal force and internal moment at a certain point. Like in this case, at point B, or at point C in this case. Okay, there are several problem example I give to you guys last week to find out the internal force and internal moment at certain point. Okay, but unfortunately, that won't be enough for us to analyze the whole structure. Okay, for example, if we have a distributed force like this, in this particular case, okay, so from x1 equal to 0 until x1 equal to a, okay, from this location until this location, there is a distributed force, constant distributed force W, okay, and at point x equal to b, okay, at this location, there is concentrated force P there, okay. Most of the time, when we deal with the structure and we deal with a complex loading, this one is not that complex, but when we deal with the loading of a structure, okay, it can be a combined loading from several different concentrated load, concentrated moment, distributed force, like that, okay, and we have to know the critical location. That's the thing that we're supposed to find out normally. Okay, where is the critical location? The critical location of a particular structure when it's under loading, and the critical location of that particular structure actually depends on the value of the internal moment and the internal force which is happening at the structure. Okay, the location where the internal force and the internal moment is maximum, okay, normally is the place where is normally the critical place. Okay, so that's why it is very important for us to find out the internal force. It can be both shear and normal, okay, and internal moment. Okay, and I have told you guys already on how to find the internal force and the internal moment. For example, last week I already teach you guys on how to find the internal force and internal moment at certain location. For example, like this particular point C. Okay, I will name it as C. Okay, point C here. Okay, last week I told you guys that in order to find the internal force and the internal moment at a certain point, like point C here, what we can do is we can do a section there, and then we can analyze the left part of the section or the right part of the section. Okay, either this part or this part. So you can do whatever you want. But before you do the section, it is better for you to solve for the external forces, yes, which is happening at the support. Okay, that's what we learned last week. Okay, that's what we learned last week. So we can find the internal force at a certain location, you can find the internal force at certain location, for example, at point C, okay, by doing a section. Okay, after you find out the external forces first, then after that you can do a section, then analyze the left part of the section or the right part of the section. Okay, that's what we learned last week. Okay, but unfortunately for us, that kind of method will not be enough to solve for the critical location. Okay, because our main aim is to find out the critical location. That's why it is not enough for us to only do a section at certain location like that. Okay, why? Because we don't know where's the certain where's the critical location is. Can be here, can be here, it can be here, it can be anywhere. Okay, it can be anywhere. And if you want to know which location that will give you the maximum internal force and the maximum internal moment, okay, like it or not, if you still use the previous method, you have to do a lot of section, which means you have to do a lot of analysis, a lot of calculation. Okay, from the first section, the value of the internal shear force is this, the value of internal moment is this. From the second section, we can get a certain value of the internal force and the internal moment as well. Third section, fourth section, etc. Okay. It will not be. It will be a problematic for us because the number of calculation that we need to do is quite a lot. Not quite a lot. It's a lot. Okay. That's why we have to find another method in order. Okay. We have to find another method in order to find out the shear and the moment diagram. Shear and moment diagram, shear force diagram is actually a diagram which show the value of the shear force, okay, at every location in the structure. The moment diagram is a diagram which shows the value of the moment at the structure at every location. So actually what we're supposed to do in order to find out the critical location is to find out first the shear and the moment diagram. And I haven't told you yet on how to find out the shear force diagram and the moment diagram. Okay, so for today, we will concentrate on how to find out the shear diagram, the shear force diagram, and the moment diagram. Okay, how to do so? Okay, later I will teach you on how to do it. Okay, so basically, later, what you will find out is a diagram like this. This is the shear force diagram of this particular case. Okay, so that is the shear force diagram, and this is the moment diagram. This diagram actually represents the shear force which is happening at the structure at every location, and the moment which is happening at every location in the structure. So for example, at point A, this one, at point A, the value of the shear force is like this. The value of the moment is this. Point A, where is point A? Point A is here. This is point A. Okay, so we can find out the value of the shear force and the moment at every location in the structure using this particular diagram. Okay, next, at point B, this is point B. Okay, this is the value of the shear force. This is the value of the moment. like that. So we can find out the value of the shear force and the moment at every location in the structure, okay, by finding the shear force and moment diagram. Okay, if you have found out the shear force diagram and moment diagram, it will be very easy to find out the value of the shear force and the moment at certain location. So, for example, previously I teach you guys on how to find out the shear force and the moment the shear force and the moment at certain point C like this, for example, by doing the section. Okay, C is in the middle between A and B, so it's around here. This is the value of the shear force at C. This is the value of the moment at C. So basically, what we have done before, it will be represented as well in the shear force and the moment diagram. Now, our next discussion is how to find this and this. Okay, how to find the shear force and the moment diagram. Basically, the concept behind it is still section. We still need to do section, but the location is uncertain, which means that we have to put the location as in variable distance, like x, like that. Okay, I will teach you guys on how to do it, but before that, I will give you guys some theory behind it. Okay, so basically, if you have a distributed force W, shear force V, and moment, okay, the equation of each of those, okay, actually is connected to each other, which means that you can derive the equation of the shear force from the moment diagram, and you can derive the equation of you can find out the equation of a moment diagram from the shear force. Okay, you can find out the equation of the shear force from the distributed force. So all of those are connected to each other. Why? Because this is like a general case. Okay, one of the general case when we have a distributed force, and this particular small element is the things that we try to analyze. Okay, if we do a section on this particular element on the left of it and the right of it, okay, this is what we will get. Okay, on the left part of the section, there will be a shear force like this and moment like this. And on the right part of the section, there will be shear force as well and moment as well. The value of the shear force and the value of the moment from the left cut and the right cut is slightly different. Why is slightly different? Because there is a W here. Okay, so there will be a slight difference there, and we name it, and we assume that the shear force on the right side, on the right edge, okay, is slightly bigger than on the left edge. So we put it as V plus dV. Although later dV there can be positive or negative, so it can be bigger or can be smaller as well. Okay, the same for the moment. We assume it to have the value of m plus dm. Okay. By using this, then we can try to do a equilibrium. Okay, we can try to use equilibrium equation to check for the equilibrium condition, because like it or not, equilibrium condition must be maintained here. Okay, using sigma fy equal to 0. Okay, what we will get is the vertical forces is only v plus dv and v, and w multiplied by dx. Okay, so this is what we will get: v plus dv plus w, okay, plus w multiplied by dx, okay, minus v equal to 0. That's why here what we will get is w is equal to minus dv plus a dx, like this. Okay, then the next one is by using sigma moment equal to 0. Sigma moment equal to 0. Okay, this is sigma moment equal to 0 from the right edge. Okay, this is what we will get. V is equal to dm per dx. Then by joining these two equations, then we will be able to get this, because v is equal is v here from the middle equation here is actually dm per dx, the first derivation of m against x. Then and w here is the first derivation of v against x minus. Okay, then we can find out that w is actually minus w is actually the second derivative of m against x, like that. So this is the equation to connect between w, v, and n. Okay, sometimes you can use this equation to solve for the discrete to solve for the moment diagram and the shear force diagram, but most of the time, without using this equation, you still be able to solve it. Okay, you still be able to solve it. How to solve it? I will teach you guys on how to solve it. But before that, I will open a Q&A session first to discuss about the things that we have that I have told you guys up until now. Anyone here want to ask question? Yep, Rizky.
I still cannot imagine what is the difference between V and V plus dV.
V plus dV, okay. V is actually the shear force which is happening on the left edge. Okay, and V plus dV is the shear force which is happening on the right edge, because there must be a difference, right? If we have a W in the middle like this. So this is like just like an assumption, Risky. So actually we can put it like this. The value of V on the left edge is V1. The value of V on the right edge is V2. But by doing so, we will not be able to find out the connection between Vm and W. That's why we assume that there is a difference between V2 and V1. The difference is here is V, and on the right edge there is a slight difference there, and the slight difference there is assumed as dV, delta V actually. Do you get it?
Okay, but I understand now.
Mhm. The same for the moment. It's just like an assumption that the right edge and the left edge, there is a slight difference between the left edge and the right edge. Value of the P and M, like that. Okay. Any other questions?
Hello, sir.
Yes, Matthew.
I have a question about vertical beams. It's hard to determine the convention for the moment
The moment.
because, yeah, how will we determine the convention sign, the moment sign
The
for vertical
convention.
beams? For internal forces, sir.
Oh, for the moment, right? It is very simple as well. So this is the same as what I told you guys last week about the sign convention. The sign convention is like this. Okay, so whenever we talk about a positive normal force, it's always tension. Whenever we talk about positive shear force, it's always giving a clockwise rotation. And whenever we talk about the moment, positive moment, it's always giving a smiling structure. So actually, you don't have to take a look at this. What you can do, right, is just try to read for this one. For example, this is the things that we talk about. And if the moment or the shear force or the normal force is on the right of the structure, on the right side, on the right edge of the structure, then positive shear force is like this. Okay. Positive moment is like this. And positive normal force is like this. And if we talk about the left edge, okay, if we talk about the left edge, positive shear force is like that. Okay, positive moment is like this. And positive normal force is like this. Okay.
Sir, I get that. But for vertical beams, how do you determine the smile structure?
For vertical beams, in that case, you can assume it first. You can assume it first. So for horizontal beams, yes, it is very simple like that. But for vertical beams, right, you can assume the positive x. Sorry, for the your direction of the for the positive for the vertical beam, right? What you can do is you can always assume where is the location of the upper parts, these upper parts and the lower parts, the imaginary upper parts and the lower parts. Okay, you can assume that this one is upper parts and this one is lower parts. So because of that, then our x will be like this. This is x direction going down. So later for this one, if you assume like this, okay, it will be like this. V going like that, positive. Moment smiley face is like this. Okay, and normal force like that. Okay, the only difference there will be the moment, Matthew. Okay, because for the moment, smiley face we can it will only be there if we know the upper part and the imaginary upper part and imaginary lower part, right? So if we assume that this one is the upper part, then this is it. But you can do the opposite as well. For the vertical, there is no sign convention for the vertical beam. But from the beginning, you can assume your positive sign like this. Okay.
So, sir, once we determine the x positive quote unquote for the rest of the vertical beams juga kayak gitu.
Okay.
How about if the beam is slightly tilted?
Slightly tilted. If it's slightly tilted, it's easier actually if it's slightly tilted, because if it's tilted like this, right? This one is upper for shear. This one is lower for shear, right? The same as this one. If it's slightly tilted like this one is upper, this one is lower, right? It's much easier. You can just use the previous one like this. This one is upper, this one is lower. But actually, there is no sign convention for that beside the horizontal beams. But in order to make it easier for you guys, when you want to do the shear and moment diagram, the first thing that you're supposed to do is to draw the positive signs like this. Okay, Matthew?
Okay, sir. Sorry, sir. So yang tilted, how do you determine which is the positive X direction?
Upper is always going like that, right? Lower is going like that. So if it's upper, lower like that, so the direction is always like this, right? To the right. Okay. So later, your positive will be like this. For this particular one, or for this one, the positive will be like this. Okay.
Okay. So for vertical, it's safe to assume salah satu aja ya.
Yep.
As long as you're consistent for the whole system.
Correct. Yes.
Okay.
So that's the thing. So it is better for you from the beginning that you state from the beginning. This is the sign convention that I use in this particular structure. Okay.
I think I did it the other way, sir.
Yeah, it's okay. But as long as later in the next problem, right? If you have a other problem, then assume it first. Okay, this is my sign convention, like that. Okay, it's up to you.
How do we like tell the or tell you how do you determine?
Just put the sign convention there. This is the sign of convention that we use for I use for this particular structure, like that. Okay, the one that has a standard is this one, only this one, the horizontal one. The vertical one, we don't have it. So that's why from the beginning, if you have a vertical one, state it from the beginning that this is the sign convention that I use for this particular structure. Okay.
So for horizontal, no need, yeah, no need convention.
Yeah, because the horizontal is supposed to follow the standard. Right?
Okay, thank you, sir.
Okay. Then we will continue, because up until now I only explained to you that in order to find the critical location, we have to find the shear and moment diagram. But up until now I only show if we have a case like this, then this is the shear force diagram and this is the moment diagram. So this is the shear force diagram and this is the moment diagram. Okay, but I haven't told you yet on how to find out the shear diagram and the moment diagram. Okay, but I told you a little bit on the connection between the shear force, moment, and distributive force. Okay, but most of the time, it is not necessary for us to always follow this. Okay, to use this all the time, because sometimes, most of the time, it will be easier for us, instead of using this equation, is to derive the moment diagram and the shear force diagram directly from the section. Okay, so this is one simple problem about the how to find out the moment diagram and the shear force diagram. Okay, so the question there is we have to draw the shear and moment diagrams for the beam. Okay, and we have to find out the location, the critical location based on the maximum moment. Okay, the critical location based on the maximum moment. For this particular case, okay, the positive is supposed to be like this, right? The positive phi and the positive moment. It's supposed to follow that sign convention, the standard sign convention. Okay. As usual, in order to find out for the shear and moment diagrams, the same as in the section method to find out the shear force and internal shear force and internal moment at one particular point. Okay, we have to find out first the reaction force at A and at reaction forces at A and at B. Okay, that's why we can try to draw for the we can try to draw for the free body diagram. I think it's not long enough. Okay, so for the free body diagram here, we have P here, we have 2P here, and we have at here we have AY, AX, and then we have QY here. Okay, so we have three forces that we have to find first: AY, AX, EY. How to find those three? As usual, we can solve for those three using equilibrium equation, right? Using sigma moment at point A. Wait. Okay, for practice, right? I think I will point out one of you to help me to solve for this. Johan.
Yes, sir.
Okay, help me to do this, Johan, the first part. Using sigma moment equal to 0, Johan.
Okay, so first we should use
Sigma
sigma
moment equal
moment
to
at
0.
A.
Yeah, that one.
Yeah.
Good. What we will get there?
So P times L per 4
L per 4, okay.
plus BY times L.
L per 4, okay. P times L per 4 plus
BY times L
PY times L
minus 2P
multiplied by
times 3/4 of L.
Yeah, equal to 0. Okay. So by solving this, we will be able to get BY, right?
Yes, sir.
What is the value of BY here?
Five per 4L, I think. I'm sorry, 5 per 4P, I mean. 5
per 4P. Okay, This one is 1. Sorry, this one is 1. This one is 4. 1, 4. This one is 6. 6 minus 5. Oh yeah, correct. And minus, okay, correct. You are correct. So Py is 5 4p, right? And then using sigma Fy equal to 0.
So we got AY from
Yeah. Ay plus p plus py. Py is 5 per 4p. And then minus 2p equal to 0, right?
Yes, sir.
What is the value of Ay here?
A quarter of P.
A quarter, positive or negative?
Negative.
Negative. Don't forget about that.
Yes,
Negative. Negative. Okay, quarter of p. Okay. So ax here. How about ax?
it must be 0.
This one is using sigma fx equal to 0, right?
Yes.
Then what we have is ax equal to 0. Okay. So now we know all the values of the external forces, right? And because of that, then we can draw for the final free body diagram. Okay. If I want to draw for the final free body diagram, it's supposed to be like this, right? Just now, what we have here is minus quarter of p, right? Then we have p here, and we have 2p here. And then last one, we have py is 5 of 5 quarter p. Okay, so this is the free body diagram, right? The final free body diagram. Correct, right, Johan?
Yes, sir.
This one is L per 4, L per 4, L per 2. Okay. Why I do it this way, later you will know why. Okay. Now, the next thing that we're supposed to do is doing a section. Okay, Johan, would you mind to point out one of your friend to help me to do this?
Okay, sir. I think I'll choose Rizky.
Rizky. Okay, Rizky.
Halo, Pak.
Hello. Okay, Rizky. In order to draw for the free body diagram, in order to draw for the moment diagram and internal force diagram, okay, we have to do a section at certain location.
Yes.
Rizky, okay. So for example, this is our first section, this is our second section, and this is our third section. Okay, and beside that, we have to assume as well the direction of x. So in order to make it easier,
Yes.
I put it this way. Okay, this is my x. This is my x definition. Okay.
Okay.
If I so everything we will cut it at distance x from the left edge. Okay, Rizky, do you
Yes,
get it,
Pak.
Rizky? Okay, now
Yes.
for the first section, this is my free body diagram. The distance here is x. Okay, the distance there is x. the distance there is x, then because I cut it in between 1 over p, so p over 4 and p there, okay, here in this location.
Yes.
So if we only take a look at this particular cut, what forces that will be there?
It's only p over 4.
Correct. So we only have this, right?
Yes.
P over 4. Okay. And whenever we have a section, as what I told you before, okay, what things that will be there in the section? Like in the
normal force, Pak.
normal force, okay then. Yep, normal force and then shear force, right?
Yes.
The direction of the positive shear force, remember?
Going up.
Always use this.
Yes.
Okay, moment. This is the positive. Remember, this is on the right edge. Shear force positive is going up or down.
Oh, down. Sorry.
Take a look at this, okay?
Yes.
We have to follow the standard.
Yes.
That's the easiest way to do it. So
the shear is going down, and
the shear force is going down.
There's a tension force to the right.
Okay, tension force to the right. And what else?
And a moment.
Moment. Counterclockwise or clockwise?
Counterclockwise.
Counterclockwise, correct. Counterclockwise moment. And then like this, normal. Okay.
Yes.
From the beginning, I will try to calculate for the normal force, because actually for this particular case, because there is no normal force involved in the free body diagram, all the normal force will be 0. Correct, right?
Yes.
Using sigma fx equal to 0, this is what we will get. Normal force will be equal to 0, right?
Yes.
Okay. And then now I want to find for phi. Which equilibrium equation that we're supposed to use?
Sigma fy equal to 0.
Okay, sigma fy equal to 0. Then what I will get there?
It's p over 4 plus phi equal to 0. So p over 4 equal to minus phi.
Okay, so p over 4 plus phi equal to 0. That's why phi, actually don't put it as minus phi equal to some, because phi is the one that we want to find.
Yes,
okay?
Equal to minus p over 4.
Okay. So that's the first thing that we get. Phi is minus p over 4. Remember, this is actually an equation, constant equation, this key. So from x equal to 0 until x equal to L over 4, the value of phi will be minus p over 4.
Yes.
Do you get it, this key?
Yes, I get it.
Okay. Now, the last one, sigma moment. Sigma moment on the left edge or right edge?
On the right edge.
Right edge. Okay. Right edge R like that. Okay. Equal to 0. What you will get?
P over 4 times x.
P over 4 times x. Okay. Counterclockwise, right?
Yes.
Okay.
And I think that's it. Equal to 0.
Now, how about m? M is there.
Oh yeah.
Don't forget.
Plus m.
Plus m equal to 0, right?
Yes.
And then, because of that, we will be able to find for the m value, right? What is the m value here?
The m value is minus px over 4.
Minus p over 4 x, like this. Okay, don't worry about the x because it's in the shape of equation.
Yes.
So later, the first equation here will work for x equal to 0 until x equal to L over 4. Not equal. I mean, it will walk from between x equal to 0 till L over 4. Okay. So this one, we will be able to find the value as well. M at x equal to 0 is equal to 0, right? We can just put it here in this particular equation.
Yes.
And M at x equal to L over 4, what is the value?
When
x equal to L over 4.
It's
just put x here, the value L over 4 there.
I see. So it's minus P over 4 times L over 4.
Yeah, so minus PL over 16, right? 16, right?
Yes.
Okay, so we know the value at this and this. Why I put it there? Because this particular equation is what you call it, linear equation, right? So
yes,
linear
yes.
equation is supposed to be in the straight line. So we can draw it there. Okay, this is the first section. Okay, actually, we can just try to draw it. We can try to draw from now for the shear force diagram and the moment diagram. Okay, so this is the shear force diagram. This is V, this is 0. Okay, and then we will try to draw the moment diagram as well. This is our moment diagram. Okay, help me again, Rizky. Just now, from x equal to 0 until x equal to L per 4, what is the value of V?
The value of V, constant.
Yeah, constant.
Minus P over 4. So
minus
it's only
P
a
over
straight line.
4.
Yeah.
So it's supposed to be a straight line here.
Yes.
I think I will use different. Yeah, this one. And the value there is supposed to be P over
Minus
4.
P over 4.
Minus
Yes.
P over 4. How about moment?
The moment will be declining.
Okay. So it's from 0
Yeah.
when x equal to 0 and minus PL over 16.
Yes.
Yeah. So the line is supposed to be like this. Okay. This value is minus PL over 16. Okay. The first section we solved it already, right, Rizky?
Yes.
Okay. Now for the second section, who you want to do you want to still doing it, or you want to point somebody else to do it for you?
I think I'm good with one more, and then I will choose my friend.
Okay, you are good with one more. Good. Then now the second section, right?
Yes.
For the second section. Okay. Then we have to draw for this part, right?
Yes. There will be a new force aided. There will still be P over 4 to the bottom in the left.
What else?
P to the top. P to going up.
This one, right?
Yes.
P going up here.
Normal force and shear force.
And moment as well.
Yes, and moment.
Okay, like this, right?
Yes, just like before.
And then normal.
And the normal will equal to 0.
Okay, so, and this is my x. And this will walks from, sorry, this one is not from 0, remember, because this one will only walks between L over 4 until L,
Over 2.
not over 2, but
L over
this
4
one.
plus L over 2 ya?
Yeah, 3L over 4, like that. Okay. The same as before, using sigma fx equal to 0, what you will get like just now, you pointed out as well, n equal to 0. Then using sigma fy equal to 0, okay, what you will get there?
Sigma fy equal to 0, we can get the value of p.
Yeah,
Oh.
phi, right? Yeah.
Yeah,
So what you have there?
So p over 4 minus p. Minus p plus phi.
Minus p plus phi.
Phi, yeah.
Equal to 0. So what
Will
is the
equal to
value of
0,
phi?
yes. The value of phi will be p minus p over 4.
So 3p over 4, right?
Yes.
Positive or negative there?
It will going up.
Positive, right?
Yeah, positive.
Positive. Okay, so this one is positive. Then now, the last one, sigma moment. Sigma moment, but now I want you to do it for the left edge.
But there will be two functions, right, for the moment?
Why two function?
Because when from the start until p.
No, from the start until p is already represented by this.
Oh, yeah.
So now you only need to concentrate between L
the x,
over 4
yeah.
until
The
3L
distance,
over 4. Yes, that one. Okay. So for this one, I want you to do sigma moment from the left edge.
Okay.
What do you have there?
So it's p multiply by x, but minus
this one. You mean this one?
Yes.
No, this one is the distance is not x, but this one is the distance L per 4.
Yeah, I mean L per 4 minus x.
Oh, why minus x? No, there is no minus x there. P multiplied by L. Yeah, P multiplied by L per 4. That's the moment. So counterclockwise is negative, right?
Yeah, I mean if you use 3L over 4, you need to
3L over 4. No, you don't have to. No, you don't have to. That's why I use the left edge. Okay. Then after that we have phi, right?
Yes.
Okay.
Phi
minus or plus
will
this
just
one?
multiplied
Minus.
by that one.
Phi multiplied by x, right? Correct or not, Rizky?
By x.
Yeah. Okay.
Yes.
And then plus moment equal to 0, right? This is the whole equation.
Yes.
But remember that phi there we have the value already. So PL over 4 minus 3p over 4 multiplied by x. Okay. Plus m equal to 0, right? Like this, right? Hello, Rizky?
Hello, Pak. Sorry, I got bad connection.
So this is it, right?
Yes, that's it.
Okay, PL over 4 going down. Sorry, counterclockwise. PL over 4 counterclockwise. Then phi clockwise, negative. And moment counterclockwise, positive.
Yes.
Okay, so now we can get the equation for m, right?
Yes.
The m there is equal to
it will equal to 3p over 4 times x.
Yeah, minus PL over
Minus
4.
PL over 4, yes.
So when x equal to 0, the value is
Minus PL over 4.
x equal to 0, the value is minus PL over 4, which is the same as this one.
Yes.
Sorry, moment at x equals to, this one is not x equal to 0, sorry. We're supposed to start it from x equal to L per 4, right?
I see.
Yeah, this one, remember.
Yeah.
So minus PL over 16, there. Hey, no, right? Actually, it's not minus PL over 16,
Yeah.
but we're supposed to put it there. If you put it L per 4 there, what is the value there?
It will be
3PL over 16, right?
PL over 16.
Minus PL over 4. What is the value there?
So it will be minus 1 PL over 16.
1 PL over 16. It's correct, right? Minus PL over
1 PL over 16.
16. Like this, right?
Over 16.
Yeah, 1/6. Okay. And then the last one is at x equal to 3L per 4. What is the value of the moment?
PL per 4. So it will be 9 PL over 4 over 16 minus, so it will be 5 PL over 16.
9 PL over 16 minus 9 PL over 16 minus
4 PL over 16. So it will be 5 PL over 16.
5 PL over 16. Plus, right?
Yep, it's plus.
Okay. Now let's draw for the shear and moment diagram. For the shear force, okay. For the shear force, now it got increased to 3p per 4, right?
Yes.
Around here. The value is 3p per 4.
Yes, 3p over 4.
Okay. How about the shear force? When x equal to L per 4 is minus PL per 16, same as before, right?
Yes.
After that, it got increased to 5 PL per 16, right?
Yes.
Okay, then roughly around here. And the value there is 5 PL over 16. Yeah. Okay, this value is 5 PL over 16. Okay. Now for the last cut. For the last cut, I'm quite lazy to do the cut from the left. Okay, for the last cut, I'm quite lazy to do the cut from the left, because if we want to do the cut from the left, we have to handle quite a lot of forces. We have 1p of 4 on the left edge, this one on the left edge, then P at L per 4, and then 2P at 3L per 4. Okay. Instead of doing so, I will do the cut, but from the right. Okay. I will do the cut, but from the right. Okay. I will do the cut from the right. Okay, still risky because in order to do this, right, I think it's better for you to keep continuing this. Okay, risky.
Okay, Pak.
Now the free body diagram, instead of doing it from the left, I do it from the right. Okay, I do it
Okay.
from the right. So this is the things that I will talk about. Okay, Rizky?
Okay, Pak.
This is the things that I will talk about. And now I have 5 per 4P and this is my
X.
L minus X.
Yeah, L minus X.
Correct, right? L
Yes.
minus X is from the right. Sorry. L minus X. L minus X. This one. So this one. Still from the left to right.
Yes.
But L minus X, right? Then what we have there is only one force. Then we can use this, right?
Yeah, shear force to up.
Yeah. Shear force.
Clockwise moment and tension force to the left.
Okay. But you understand why we use that instead of the other sides, right? Because now the cutting side is on the left. That's why, like it or not, we have to use this.
Yes.
Okay, we have V, we have N, and we have M. Using the same sigma Fx equal to 0, what we will have is N equal to 0. Sorry. Then using
Sigma Fy equal to 0, we can found the V equal to minus 5 over 4P.
Minus 5 over 4P. Then
using moment on the right edge, we will get
moment. Don't use the right edge. Use the left edge.
Yeah.
Because that one is easier.
So it will be 5 over 4P times L minus X.
5 over 4P times L minus X.
Then plus moment equal to 0.
Plus or negative?
It's negative.
Negative.
Yeah.
So our moment equal to?
Moment will equal to 5 over 4P times L minus X.
Okay, so 5 over 4P. Okay, when X equal to, and this one will works for X, 3L per 4. Until L. So the first one that we're supposed to check is moment at X equal to 3L per 4. What is the value there?
The value at 3L over 4 is 3L over L.
5 over 16, right?
Yes, L over 16. Yeah.
Okay, 5L over 16.
Right? Yeah, I mean 5L over 16.
5PL over 16. Correct.
Correct.
Then the value at x equal to L is
X equal to L 0.
0. Correct. 5PL over 16 is already there. Okay. So the moment is actually easier to draw here because we just need to connect it to 0. Like this, right? The value here is the same as before, right, Rizky?
Yes.
But now we have a problem because the Fy is minus 5p of 4, which is out of the charts, right?
Yes.
So later when you draw it, you have to prepare for the charts. So this one is actually, the scale is actually incorrect because the value here is supposed to be 5 over 16, right?
Yeah.
This one, 5p over, sorry, 5p over 4. 5p over 4 minus. So it's supposed to be slightly incorrect here, this one. Because that one is supposed to be going down even more, 5 times of this one. But because I don't have a space there, so I draw it there. Okay, Rizky, do you understand, Rizky?
Yes, I understand, Pak.
Yeah. So actually, the good thing of helping me doing the things directly is, for sure, you will get more understanding than the others because you try directly by yourself.
Yes.
So this is the our shear force and moment diagram. But remember, we haven't answered the question yet. The question there is determine the maximum bending moment and max and its location. What is the answer, Rizky, here?
The maximum will be 5PL over 16.
Yep, 5PL over 16.
And
the location is?
will be 3L over 4.
Yeah, 3L over 4. So the location will be here, right?
Yes.
And the value will be 5PL over 16. Like that. Okay. Anyone here want to ask question about this first problem? Okay. Until tomorrow, most of the time, I will use most of our class time to practice for this. And after the class today, I will post some of the video of the practice problem on this particular internal force and internal moment, like that. Okay, because I have a lot of practice problem for this, which I used to teach last year, and I have the YouTube video as well. So I will post it in our NST, so you can watch the video. Okay, anyone here want to ask question about this? So about internal force, most of the time we have to find this. Okay, internal force diagram and internal moment diagram. Anyone here want to ask question? No? Is it quite clear?
It's quite clear, sir.
Okay. How about the other? Tiko Rifanto. Do you understand about this, Tiko?
I understand, sir.
Irfan Mutakin? Supposed to be okay, right? And
Yes, sir.
Pasha Firmansyah.
Yes, sir.
Do you understand?
Understand. Yes.
Good, good. So in that case, I think I will continue our discussion with the next problem example. This one, it is slightly different because now we have concentrated force and we have the distributed force as well. Okay, so for this one, okay, Rizky, would you mind to point out one of your friends to help me to solve for this?
Sure, Pak. I think I will choose Shabina, Pak.
Sabina. Halo Sabina. Halo Sabina. Where are you, Shabina? Don't say that you slept again. Seems like that. Okay, Rizky. Shabina seems like she.
Okay, I will.
Yes, sir.
Okay then. Where were you, Sabina?
Kayaknya tadi nggak kedengaran, sir.
Okay. So for this one, I will ask you first, how many sections? If the previous problem, we need to use 3 sections, right? For this particular problem, we have to do a section here, here, and here in order to have the complete internal moment and internal shear force diagram. For this one, how many sections that we need in order to solve for this? Shabina. Hello?
Sorry, sir. I don't know.
You don't know?
I think it's 2.
Yes, correct. It's supposed to be 2, here and here. Okay. So basically, the number of section that we're supposed to use in order to solve the problem, it depends on the number of discontinuity. Okay, it depends on the number of discontinuity. When we talk about discontinuity, discontinuity will appear when there is a concentrated load, concentrated moment. That's it. Okay, when there is a concentrated load and concentrated moment, and the initial of the distributed force. Okay, the initial of the distributed force. So when we talk about this particular free body diagram, there is a concentrated load on the left edge, concentrated load here, here, and here. That's why our moment diagram have to follow that as well. So when we decide about the section, okay, the first section supposed to handle between this concentrated load, these 2 concentrated load. Okay, the second section supposed to be there in order to handle the parts between this concentrated load and this concentrated load. And the last section, okay, supposed to be used to handle the location between this concentrated load and this concentrated load. Do you get it, Shabina?
Yes, sir.
Okay. Now, for this particular things, right? If we draw the free body diagram, okay, if we draw the free body diagram, it's most likely become like this, right? This. There is a 2 kilonewton here, and there is a distributed force here. And because there is a fixed clamp there, at the end, there's supposed to be there's supposed to be a reaction as well, right? Okay, it's supposed to be reaction force V and then moment as well. Okay, this is supposedly the free body diagram, right, Sabina?
Yes, sir.
Now, try to take a look the discontinuity that I talked about just now. Discontinuity can be discontinuity is it will be there because concentrated load, concentrated moment, and the start of the distributed force. So this one is there will be a discontinuity there, right? This one and the start of the distributed load here and here as well, right, Sabina?
Yes, sir.
Yeah. So there will be 3 locations when it has a discontinuity. So, like it or not, the section supposed to be done in order to handle those things, right? That's why we have to do a section here between the concentrated load and the initial of the distributed load, okay, to handle the equation of the distributed, the equation of the moment and internal moment and internal force between those 2 locations. And the second section is supposed to be here to handle the internal moment and internal force between those 2 locations as well. Do you get me, Sabina?
Yes, sir. So all the part can be
Hmm.
calculated. Yes.
Yeah. So now we need 2 sections there. But before that, we have to calculate first for the value of the sorry, this one is not V and M, but this one is supposed to be By and moment at B. Okay. But the first thing before that, we have to find out the value of By and moment at B, right? Correct, right, Sabina? Before doing the section, we have to find out all the external forces first, right?
Internal forces or
External first. So before we find out for the internal, we have to make sure that we got all the external forces. That's the first rule, Sabina. Okay.
Okay.
So
Okay.
By and MB there, we have to solve it first before we can do the section. Okay, remember, right? First, we have to solve for the external forces before we can do the section to solve for internal forces. Okay, Sabina?
Yes, sir.
Now, how to find out for By and MB? Halo, Sabina?
By using sigma moment.
Yeah, sigma moment is to find out for MB, but how about to find how about By?
And sigma Fy.
Okay, yes, correct. Sigma Fy equal to 0 to find out for By. Okay. What you have there for sigma Fy equal to 0?
By and
By positive
minus,
going up. Okay, minus minus 2 kilonewton. Okay, and then the distributed force as well. Don't forget about that. The distributed force is going down, so it's supposed to be minus 1.5 kilonewton per meter.
Yeah, okay.
But you have to multiply it by this one, the length, right?
Yeah. to calculate it MB.
Yeah, multiply by 2 meter equal to 0, right?
Yes, sir.
So Py here is equal to Py minus 2 kilonewton minus 3 kilonewton equal to 0, right? So Py there is supposed to be equal to what? What is the value of Py?
5 kilonewton.
5 kilonewton. Okay. And now, how about MB? How to find out for MB? Hello, Syabida?
For the MB, using sigma moment equal to 0.
At which location?
Is it from point A?
You can do it from point A, or the easiest one supposed to be from point B. Actually, both supposed to be okay. Okay. Let's use sigma moment at point B.
At point B.
Okay, equal to 0. Sigma moment at point B equal to 0. What you have there then?
It's minus 2 kilonewton point 4 m.
2 kilonewton multiplied by 4 meter. What else? Counterclockwise positive then in this case. Okay, what
Yeah.
else?
And
From the distributed load?
1.5 kilonewton. Plus 1.5.
Remember, this one is distributed load. So you have to find out the concentrated load first, right?
Oh,
The concentrated load is...
It's 3 kilonewton
Okay.
point
3
2 m. It's plus,
3
yeah.
kilonewton, 0.2 multiplied by 2 meters or 1 meters. The distance from here, and the centroid is supposed to be in the middle, right?
So it's 1.
1 meter. Okay, remember about this concentrated load. Okay, Shabina,
Yes.
you have to practice more about the concentrated load.
Yes, sir.
Okay, this one is 2 kilonewton multiplied by 4, and 3 kilonewton multiplied by 1. And what else? The moment there, we have MB as well, right?
Yeah.
Okay, plus or minus for MB?
Minus.
Minus MB equal to 0. That's why we have MB is equal to
11.
8 plus 3, 11, yes.
11 kilonewton
11
m.
kilonewton meter. Okay, so we have found the Py and we have found the MB as well, right? Now I will redraw with again 2 kilonewton, 1.5 kilonewton per meter, 5 kilonewton going up, 11 kilonewton. Okay. So this is our free body diagram. Just now we have 2 kilonewton going down. And then we have distributed force here. 1.5 kilonewton per meter. Then at the edge here, we have 5 kilonewton. And just now we have 11 kilonewton meter. Right? Sabina? Correct, right?
Yes, sir.
And
Yeah.
now, as we discussed before, we will have a two section. This is the first one, and this is the second one, right, Sabina?
Yeah.
Okay. Now let's handle the first section. This part. What forces that we have there in the first section? Hello, Shabina?
The only force
Is 2 kilonewton, right?
Yeah.
2 kilonewton. But here, as usual, we will have a reaction there, right? Internal reaction there, right?
Yeah.
Okay, and the positive is supposed to be? We have phi, we have m. What is the positive for phi?
Phi downward.
Phi downward, correct. How about m? Counterclockwise or clockwise? Remember, m is positive when it gives a smiley face.
So it is counterclockwise.
Counterclockwise. Okay. For normal force, I will skip it because anyway it will be 0 there. Okay. And this particular equation will works from x equal to 0 to x equal to 2 meters.
Yeah.
Okay. Now, let's calculate for phi first using sigma fy equal to 0. What is the value of phi? Hello, Shabina? Hello, Shabina?
Phi
What is
is
the
equal to 2 kilonewton.
actually it's not equal to, so you're supposed to draw it like this: 2 kilonewton going down plus phi equal to 0, right? So phi equal
so
to,
it's minus 2 kilonewton.
yeah, correct. Then using sigma moment on the left edge equal to 0. What you have there? This one is x, always x. What is the value there?
So it is 2 kilonewton point x minus m equal to 0.
Phi is minus. You are calculating for phi here, right?
Yeah.
But phi is minus. So it means that the actual direction is going up. So yeah, we can calculate it. 2 kilonewton multiplied by 2 meters. It's counterclockwise plus moment. It's counterclockwise as well, equal to 0. Correct, right?
Yes.
Okay. And then we have the moment. The value of the moment is equal to, yeah. This one is not 2 meters. Sorry. This one is supposed to be multiplied by x, right?
Yeah, x.
So the value of m is equal to
Minus 2x
2x
kilonewton meters.
kilonewton meter. Yes, correct. So we have for x equal to 0, okay, the value of moment will be 0, right? And for x equal to 2 meters, the value of m will be 4, sorry, minus 4 kilonewton meter. Correct, right? Hello, Syabida?
Wait, sir. I'm still
Yeah.
processing.
Hmm.
Yeah.
Okay, so that's the first section, Sabina. Now let's go for the second section first before we draw it. Okay, for the second section, I think I will ask you to draw for the from the right. So that one. Okay, so it's supposed to be like this, right?
Yes, sir.
We have 5 kilonewton and we have 11 kilonewton meter, and then we have distributed load. .5 kilonewton meter. Okay, 1.5 kilonewton per meter. And then in the section there, left section there, what we will have there? We will have V and moment. But what is the direction?
The V, is it also going down?
No, it's not. Remember that it's supposed to give a clockwise rotation.
So it's upward.
Yeah, V upwards and moment. Smiley face. Remember, moment is always giving a smiley face. So moment, clockwise or counterclockwise?
Clockwise.
Clockwise, correct. So this is the free body diagram that you're supposed to solve, and it will walk from x equal to 2 meters to x equal to 4 meters, right?
Yes, sir.
And here, the distance here, from here to here, is not x anymore because x is from the left, okay? Remember the x is from the left. So this one is not x anymore, but 4 meters minus x,
Okay.
okay?
Okay.
Now let's try to calculate the v first, as usual. Sigma fy equal to 0. What you have there?
V and
V plus 5, right?
yeah,
Going up, and then distributed load going down.
minus 1.5.
Minus 1.5 multiplied by?
Is it 2?
No, it's not 2. The distance there is 4 minus x.
I forgot
For
the
me.
distance.
Okay, so something like that. Okay,
Yes, sir.
okay, so 4 minus x equal to 0. So then our v value will be minus 5 kilonewton plus what's it, 6
6
kilonewton
minus 1.5x.
6 minus plus, okay, plus minus, yeah,
Oh,
minus
minus
1.5x. So the v value is supposed to be
1 minus 1.5x.
1 kilonewton minus 1.5x. Okay, correct. And now using sigma moment,
equal to 0.
Sigma moment on the right. Sorry, you want to use the left side or right side? I prefer the left side. Okay, sigma moment from the left side equal to 0. What you have there?
M and
M, okay, M, then what else? M clockwise positive and
V plus V point.
oh no, phi, because it's from the left side, so from here. So phi there
Yeah,
will not be
yeah.
there.
So it's 5.1.5. Sorry, 5.4 minus X.
Okay, 4 minus X, and it's supposed to be minus because it's counterclockwise, right?
Yeah.
Okay, and then plus 11, right?
Minus,
Supposed to be there.
yeah. Oh yeah.
Plus 11 because it's clockwise, and then there's supposed to be a clockwise moment. Okay, correct, positive. 5 kilonewton negative because it's counterclockwise. Okay, and then 11 kilonewton is supposed to be clockwise as well, positive. Okay, and then from 1.5 kilonewton per meter, it's supposed to be clockwise as well. So 1.5 multiplied by 4 minus X, it's supposed to be the force, right? This one. And the centroid is supposed to be in the middle. The centroid here is supposed to be in the middle. Okay. So the centroid is supposed to be in the middle. So it's supposed to be multiplied by the distance there. So it's supposed to be multiplied by 4 minus X divided by 2. So 2 minus X per 2 equal to 0.
Mm.
Do you get it why it is like this? Because this one is the force. Okay, multiply by the moment arm there. The moment arm is supposed to be from the middle to the left, right?
Okay, sir.
Hmm.
But I'm still processing the 2 minus X per 2.
2 minus X per 2 it comes from here. This one, the distance from here to here. To the middle, to the centroid here. Because the distributed force multiplied by 4 minus X. Okay, the location is supposed to be at the centroid, right?
Oh, yes, sir.
Okay, multiply by the moment arm. And the moment arm is supposed to be the moment arm there supposed to be half of the 4 minus X, correct, right?
Yes, sir.
Okay. Okay, I think I will write it down again here. Plus 1.5 multiplied by 4 minus X multiplied by 2 minus X per 2 equal to 0. Because later we will use that side to write down our okay. Now, what is the value of our moment?
Um, 20 minus 5x. 20 minus 5x.
Yeah.
Minus 11. Minus 6 plus 1.5x.
This one we have
sorry.
to do it together. So minus 1.5 multiplied by 4 minus X multiplied by 2 minus X per 2. Like that. Okay, this one is supposed to be equal to 0. Okay, so our moment is supposed to be like this. Actually, we can, sorry, it's not equal to 0. But actually, we can try to simplify the form later. So this is supposed to be m equal to 20 minus 5x minus 11. Sorry, minus 5x minus 11 is supposed to be plus 9 minus 5x plus 9. Okay, minus 0.75 multiplied by x square.
8
Yeah.
minus 4x plus x square minus 2 per 2 divided
Yeah,
by
x
2.
square. Yeah, no, I mean per 2 yeah, the per 2 I put it as outside already. So x square.
X square minus 8x plus 19.
For x
16.
minus. Okay, yeah, right. Minus 8x plus 16.
Yeah.
Like this, right?
Yes, sir.
So this is all the equation. So you don't have to simplify it again. But remember, this is the equation now become quite complicated because we have a quadratic equation here. Okay, and the quadratic equation is in minus form. So it's supposed to be going down, slightly down. Okay, and now let's draw for the moment diagram and the shear force diagram. Okay, the shear force diagram is the value is constant minus 2 kilonewton, and then linear going down. Linear going down from minus 2 kilonewton until when x equal to 4 minus x equal to 4 meter. Equal to 4 meter. When x equal to 4 meter, it's supposed to be minus 5. This one is supposed to be minus 5 meter. Sorry, minus 5 kilonewton. So our phi diagram will be like this. Okay, the first one will be minus 2 kilo. This one will be minus 2 constant. And then will be linear until it reaches minus 5. So this value is minus 2. This one is minus 5. Okay, that's our phi diagram. Our moment diagram now is slightly more complicated. Okay, slightly more complicated because
Because of the x value.
yep, correct. Because there is a distance there, right? From 0. Okay, this one is the moment diagram. From 0 at x equal to 0, yeah. Then minus 4 kilonewton meter at x equal to 2 meter, yeah. So it's linear. Then after that, it will follow this particular equation. Okay, it will follow that particular equation. Okay, at x equal to 2 meters, at x equal to 2 meters, this one is supposed to be minus 10. At x equal to 2 meters, the value is supposed to be the same because there is no nothing there. And at x equal to 4 meters, would you mind to calculate it for me? At x equal to 4 meters, what is the value of our m here? Shabina?
Which one, sir?
This one. This one. But at x equal to 4 meters.
Okay, wait, sir. I'm using calculator.
This one is supposed to be minus 20 plus 9, so 11 minus 11. So this one is supposed to be minus 11 minus this one.
Minus 3.
16, 36.
Minus
Zero.
12.
Mhm.
And
Minus 12. Supposed to be the value is minus 12. What?
1 sir.
Hah?
Kan 0,75 kali 16 ya.
This one is 16, and this one is minus 32, right?
So you calculate
This
yang
one is
dari dalamnya dulu ya.
Yeah,
Oh.
16, 16. So this one is supposed to be 0, right?
Yeah.
So the value is supposed to be 11, right? Correct, right?
Oh yeah, 0. So yeah, the m supposed to be 11.
11, right?
11.
Minus 11. Okay. So roughly, because this one I supposed to find the other value first. Okay. Minus quadratic minus is supposed to be like that. Okay. So I think it's supposed to be like this. This value is 4 kilonewton meters. And this one is supposed to be 11. That one. But remember, this equation is supposed to be quadratic. So it's slightly curving like that.
Okay.
Okay. I think that's all. Thank you, Sabina. It's already noon, and I think it's time for our discussion today. And tomorrow we will continue with several other problem example. Please check your MS Team because after this I will post several videos on several other problem example
Okay.
and today's class as well. Okay.
Okay, sir. One thing, sir, before I forgot, I don't know if you already mentioned it or not, but I already told you that I forgot to mark my attendance list.
Okay.
Last
think-
Thursday.
Sir,
Last Friday, sorry.
Okay. I think in that case, it's better for both of you to discuss it with me at the beginning of the class tomorrow. Okay. At the beginning of the class tomorrow, because it's already noon right now, so we will not have time to discuss more. Okay.
Okay. Thank you, sir.
Okay. Yeah.
Okay, thank you, sir.
I think that's all for our discussion today. Okay. See you again tomorrow morning. Okay. Our discussion will still be at the same for the same topic. Okay, but we will do several other problem example. Okay. See you guys tomorrow. Bye.
Thank you, sir.
Thank you, sir.
Bye bye.
Thank you, sir.
Thank you, sir.